Hi, good afternoon. My name is Adolfo Herna. Welcome to my poster exposition related to metamaterials. Let's go for it. And here we go. Well, I will speak about two different transversely isotropic metamaterials, quite similar between each other. However, one has hexagonal symmetry and the other has square symmetry. My name is Adolfo Ayuso, and my guidance in this project has been Federico Sabina, who happens to be a researcher at IMAS, and that is the Applied Maths Institute of UNAM. And I am a student, a master student of the associated program. So first we have the index. And first I will give an introduction, definition of what a metamaterial is. Then I will give the general outlines of our research. That will be the main part of this small talk. And then I will briefly speak about the mathematical part of our work for the first and second case. Finally, I will show some plots and the conclusions. Well, first of all, what is a metamaterial? A metamaterial is, as the name says, an engineered compound with some convenient qualities that don't occur in the natural ones. Namely, they affect the sound and electromagnetic waves that happen to travel throughout them. Some of their applications are the construction of optical filters, medical devices. As you can see, they are useful in phenomenon including waves in general. Our research. Well, first I will give our original goals and the motivations behind them. Of course, we wanted to mathematically describe the proposed compounds in order to know if they would be useful for daily life or for experimentation. And we wanted to analyze their behavior as both of the rigidity modules of the ideal fluid containing the fibers tend to zero. Why? Well, in order to test to what extent the qualities of the compounds still remain interesting or useful, and to compare both cases in the limit. Now, here's where the real work began. We studied the compounds generated by this periodic cell. As you can see, it's an hexagon. We obtained the effective coefficients of it by using the asymptotic homogenization method. Here are the effective coefficients, and as you can see, both M1 and P1 are involved in their definitions, as well as many others, many other variables. Of course, M1 and P1 are the rigidity modules of the ideal fluid, and so if we want to know how do the effective coefficients behave when the rigidity modules disappear, we need to calculate the corresponding limits when both M1 and P1 tend to zero of all of these quantities and these ones. So we did it, and we obtained these new expressions that compared to the original ones are quite simple. So for the next case is we have actually the same. We study the compound generated by this periodic cell that is now a square. We obtained the effective coefficients by using the asymptotic homogenization method. Again, we calculated the limit of those expressions and this one, and of these expressions when both M1 and P1 tend to 0, and we obtained more convenient formulas. Here they are. Finally, we have some numerical iterations for the specific case when the fluid is glycerin, and when the fibers are made of graphite. Here are the corresponding effective coefficients. And here you can see the behavior of the three non-zero effective coefficients as the volume of the graphite fiber increases. And finally, what did we learn? Well, three things. First, that the obtained metamaterials are in fact transversely isotropic metafluids, because the effective coefficients related to M and P are actually 0. And that the reduced coefficient expressions and the limit are easier to handle than the original ones. And in the limit cases, both compounds behave the same. Here are the reference. Well, if you have any questions, here is my email, and here is the corresponding bibliography. Thank you so much for your attention.